Hello everybody. Today I'm going to actually start with the rate equations that Mr. Einstein considered for a two-level atom for interaction with light. And after that I'm going to go into writing these rate equations in a different form. So let me actually tell you that if you consider an atom with only two energy levels E1 and E2, then we call that as a two-level atom. And usually we denote the energies of these as E1 and E2. And if you take a collection of these atoms in some volume V, and if you count them, uh, then the number of those atoms divided by the volume is what we write as capital N, and this is actually the number density, total number density of the atoms. So the dimension formula for this usually is L power minus 3, L minus 3. You remember dimension formula MLT, we write for mass, length and time. So this is actually the dimension formula for the total number density of the atoms. And in some atoms what can happen is the electron can actually sit in the lower level, lower energy level. And if you count, if you actually count the number density of those atoms, then we usually denote that as N1. And this is also referred as the population of level number 1. So even for this also the dimension formula is same as L power minus 3. And in some atoms the electron can actually sit in the upper level here. So for such atoms, the number density is usually denoted as N2. Okay, so after knowing these N1, N2 and N, of course N should be equal to the summation of N1 and N2. So Einstein wrote the rate equation because of a spontaneous emission as a dN1 by dt is equals to minus a into, sorry, here it is N2 because that's the population which decreases because of spontaneous emission. So here it is 2 as well. So dN2 by dt is equals to minus a into N2 is for this spontaneous emission process. And for the stimulated emission process, the equation Mr. Einstein wrote was dN2 by dt is equals to minus some coefficient called B21 coefficient and rho, that is actually the spectral energy density of black body, because we consider the whole sample is in contact with the black body. Whole sample of atoms is in contact with the black body. And then here also N2, and this is because of stimulated emission process. Okay, and for absorption he actually considered the decay happens for the lower energy, the population of lower stage. That's why we write dN1 by dt, and this is minus B12. This is actually Einstein's one of the coefficients, and then rho again here and N1 here, and this is because of absorption process. Okay, so he wrote these rate equations in this form, and at the end of this lecture we again see writing these in a slightly different form. But anyways, let me go ahead with Einstein's derivation of relationships among these A, B1 to B21 coefficients. So Einstein combined these two equations and wrote one master equation, one big equation for dN2 by dt. So if you write it like this, then it will be having the first term as minus AN2 and second term as B21 rho and N2 in the right hand side, and left hand side it will again have same dN2 by dt. And so we can call this one as number 1 and this one as number 2. So at thermal equilibrium, what we expect is dN1 by dt being equal to dN2 by dt. So if you equate this equation number 1 and 2, then we can actually write minus a n2 minus b21 rho n2 equal to minus b21, sorry, b12 rho and n1. So we can rearrange these terms. We can send the first term in the left hand side toward the right side, and we can bring whatever is there on the right hand side now towards the left side. And if you even take the rho as common factor out, then we get b12 in 1 minus b21 into n2 being equal to a n2. This is what we get. And let me erase the upper part because I need space for writing the further steps. So this rho, we can write this expression for rho from this, the spectral energy density. So this will be equal to a n2 here, and we can actually bring this guy as common factor out. So if you write b21 into n2 outside, then this should be b12 divided by b21 here, and n1 by n2 here, and minus 1. This is what we get for rho. And we can cancel out n2 over here, so n2 and n2 will get cancelled because it's there in both numerator and denominator. So we can write rho is equals to a divided by b21 in the numerator, and in the denominator we can write b12 divided by b21 into n1 by n2 minus 1. But from the Boltzmann statistics, the ratio n1 and n2, the ratio of n1 and n2 can be written as degeneracies of these labels. If you label as g1 and g2, then it should be equal to g1 by g2 into exponential e2 minus e1 divided by kt. So we can write this ratio of n1 and n2 like this in terms of degeneracies of these levels number 1 and 2, and also the energies of these levels e2 and e1. I mean energies e2 and e1 of the levels number 1 and 2. So if you substitute this ratio in the upper expression for rho, then we can actually, I don't know if I come here I may get shadow, that's why I am actually sticking to stay here. So if you write it so, then rho will become a divided by b21 and all thing divided by b12 divided by b21 into g1 by g2, the degeneracies of levels 1 and 2, and exponential. We can even write this e2 minus e1 as h nu. So if you write it so, then it is h nu by kt and minus 1. This is what we get for rho. Okay, so I'm going to erase this part here because my body is really small and I need space for writing. So, but from the black body radiation topic, the rho should be equal to some quantity, that is rho is 8 pi nu square by c cube into h nu divided by exponential h nu by kt minus 1. This is actually from the topic of black body radiation that is explained by Mr. Max Planck after considering that energy of light is quantized and with the label photon. This is the expression which he got. So if you compare this equation and Einstein's equation, so this is actually Max Planck's equation and this is actually Einstein's equation. So if you compare these two things, the numerators of them we can actually see this whole thing should be equal to just this quantity here. So we can write A divided by B to 1 is equals to 8 pi H, also we can take inside, and nu q divided by CQ. This is actually we can call as some equation number 3. And if you actually see, one is here, minus is here, and exponential this one. So this entire thing should be just equal to whatever factor, which is actually 1 in multiplying to this e. So this entire thing should be equal to just 1. So this B12, we can write G1 here I think, and G2 into B21 being equal to just 1. So this we can call as number 4, and equation number 3 and number 4 are actually called the relationships among Einstein's coefficients. So from these things we can actually say our G1 into B12 is equals to G2 into B21. So we remember this relationship, which we'll use sometime later in this lecture only. So let me actually erase this one and go quickly into writing the rate equations in a different form. So the first rate equation which we had for spontaneous emission, that was in terms of a coefficient for d and t, dn2 by dt, which was this one. Now we write instead of a, we actually write some kind of 1 by tau, which is actually the characteristic lifetime of level number 2. So this time is actually, dimensional formula for time is actually t. Dimensional formula for this a coefficient should be simply t power minus 1. This is actually the dimensional formula for a coefficient of Einstein. Anyways, I may not actually need this thing straight away here, but if you replace this a by tau, we can actually see that this is becoming 1 by tau. And of course, this is the expression which people use while talking about the rate equations for 3-level system, 4-level system. So which will come in this series of lectures at some point of time. So anyways, this is actually the first rate equation, that is because of spontaneous emission process, written slightly differently than Einstein. And then for stimulated emission, what we write is we write this equation as W21 and N2. So earlier Einstein wrote the same equation using B coefficients and rho, because he considered that his sample of atoms was in contact with a black body. But now we are not taking that condition anymore. We are saying that sample is just there and we don't have any black body interacting with it right now. So that's why we wrote it like this. So this one is because of stimulated emission process. And we can also write similar kind of expression for absorption involving the N1 coefficient here, N1 term, N1 quantity. So this will be minus W12 into N1, and it is because of absorption process. So if you actually compare these with Einstein's equations, at least if you compare this second equation rewritten, let me use the space right here itself, I think. So if we use this space here, Einstein's version of this equation was minus B21 rho and N2, and this equation in Einstein's version was minus B12 rho and N1. These are actually the terms used by Mr. Einstein. And what we do is we actually write this sigma W21 as a product of flux of incoming photons. I mean, in spontaneous emission, we actually get photons emitted from the atoms of the sample, and if you count those photons coming out, and that's what we can label as n. N photons are coming, and if you actually divide that by the time you observed the counting, so that is actually you can write as t, and you can actually count them in some kind of cross-sectional area. So if you divide that area, then it is actually a number of photons coming per second per unit cross-sectional area normal to the propagation of the photons. So that's what we actually call as flux of the photons. And this flux, if you worry about the dimensional formula, then this dimensional formula should be simply for T it is capital T, and for area it is actually L squared. Area is actually length into length, that's why L squared. And as these things are actually in the denominator, we should be writing T power minus 1 and L power minus 2 as the dimensional formula for flux of photons. And we also multiply this thing by some factor called sigma, and with the suffix 21, and the sigma is actually called as the cross-sectional emission cross-section. And that's because if you actually calculate the dimensional formula of sigma 21 using this rate equation, we'll be seeing that it will get L squared as the dimensional formula. That's why we actually call this thing as some area kind of term, and especially emission cross-sectional emission cross-section. So we write like this for W21, and similarly we write for W12 using the flux of photons. Oops, sorry for that kind of noise. And for W12 also it is F into sigma 12, and this is what we use. But we knew from if you actually kind of compare this and this and this, we can actually write W12 should also be, wait a second, let me start with W21 first. W21 should also be simply B21 into rho, and W12 should simply be B12 into rho. So, but we had this condition, that is G1 into B12 is equals to Z2 into B21. That is actually from Einstein's relationships among B12 and B21. So if you write this B12, this should be equal to G2 by G1 into B21. So, but from this expression, B21, wait a second, B21 is simply W21 divided by rho, and from this one, B12 is W12 divided by rho. So if you use these things in this expression, let me actually erase the space here. So if I use this expression and this expression wait a second, which one? Yeah, these two things in the last expression. In this, if I use this one and this one in this one, so I will get W21 divided by rho. That's actually, wait a second, it should be this one, right? W12 divided by rho being equal to G2 by G1 into B21 is W21 divided by rho, and I can cancel out rho on both sides. So I can just simply cancel out these things, or maybe I can erase this. So if I erase this one, I will get W12. Of course, I wrote this thing as a product of flux of photons into the cross-sectional area for absorption. And this one is Z2 by Z1 into same kind of thing, flux of photons into emission cross-section 2-1. So if I can even cancel out F on both sides because it is there in left hand side and also right hand side. So I may even simply erase this term here. So I will get sigma 1 to being equal to G2 by G1 into sigma 2 1. And of course I will use this factor, this expression in the explanation of theory of laser, which is our next topic. Okay, thanks for watching, and bye bye for today.